In Oppenheimer, Christopher Nolan takes his audience on a visually captivating ride of the history and science behind the Manhattan Project, but also the internal struggle of a man at odds with himself when creating the first atomic bomb in the 1940s. Professor Jason Donev, PhD, Faculty of Science at the University of Calgary, joins me to delve into the pioneering strides of nuclear fusion and the science behind the iconic figure in film, Oppenheimer, along with discussing recent fusion advancements and the development of small modular reactors that could potentially power a home of 4 people for over a century. Join us as we get rebelliously curious. Jason, thank you for joining me on Rebelliously Curious today. As I was saying to you before we jumped on the mic and started recording, I've been wanting to have a conversation with someone about fusion and the breakthrough technology around fusion for a very long time. So thank you for joining me today.
I'm excited to talk to people about what's happening in the nuclear world with Oppenheimer coming out and being a phenomenal success. I mean, not as big as Barbie, of course, but what is. But with Oppenheimer suddenly turning into a major motion picture, and a lot of governments in the US, in Canada, state governments, provincial governments, other governments elsewhere in the world, talking about building small modular reactors, breakthroughs in the fusion space. This is an exciting time to be working in nuclear, to be talking about nuclear, to be educating students about nuclear, just knowing that the students that I'm teaching are going to be playing key roles in developing new medical isotopes, coming up with new techniques, and building and designing these new nuclear reactors. They're going to literally change the world. It is just so exciting, and I hope I get to live long enough to see all of it happen.
Me too, because and we'll get into the breakthrough technology of fusion and that timeline, because I have heard that they said 50 to 60 years, but now I've heard it's actually going to happen maybe in the next decade or two. But we'll get into that. For maybe people that are new to the concept of fission and fusion and what is happening with breakthrough technology, can we just start in minimal form? Just what is nuclear energy, and then what is fission versus fusion? But we'll start with what is nuclear energy.
So, going back to your K through 12 education, don't believe atoms; they make up everything.
Right.
So everything that we interact with is made of atoms. You, me, the chair I'm sitting on, the microphone you're talking into, the computer I'm looking at. Everything is made of atoms. So inside of the atoms, you might remember that the atoms have the electrons going on around the outside, and then deep inside of the atoms, you have a nucleus. So what we're talking about is things that are happening inside of that nucleus. Chemistry is what happens when those electrons do things, and the nuclear physics goes deep inside. Now, what I mean by deep inside, so I've got a little model of a nucleus here. We've got 2 protons, 2 neutrons. We'll play with this a few times over the course of the conversation. And this little model of the nucleus. Now, the pictures that you see in, say, a grade 6 textbook will take a model of a nucleus like this, and it makes it look like the electrons are here, and they're not. If this was the size of my nucleus, the electrons would be almost a kilometer away.
Oh, wow. Okay.
So these things are really stupidly tiny. I mean, atoms are really small to begin with, right? Like if you take the same ratio of how big you are to how wide one of your hairs is, and then you take one of your hairs and you go down that same ratio, then you're getting the atomic scale. And you go down that ratio again, and you're getting to the nuclear scale. So we're talking really small, okay? Now, inside of that, you have protons and neutrons. The protons, which I always use red, it's just a personal preference, that protons are not actually red. I've had to explain that a few times. They're not actually red. But protons determine what atom you have. So if you've got carbon, you always have 6 protons. If you have nitrogen, you always have 7 protons. And for hundreds of years, alchemists tried to change one element into another. And because all they could do was play with the electrons, they weren't able to do that. Now enter Ernest Rutherford, who was originally from New Zealand, but did much of his most important work here in Canada at the University in Montreal. So while he was there in Montreal, he discovered half-lives, he discovered alpha, beta, and gamma radiation, he named them, and he was the first person who was actually turning one element into another. So he was doing alchemy just like the medieval scientists have been trying so hard to do for centuries. And he was also able to start explaining why it's almost impossible to do that. Now, fission and fusion are actually changing one element into another. So we're talking about, doing some almost magic, if you will. Now, fusion is you have two nuclei and then you stick them together. They fuse together, and that's why it's called fusion. And then fission does exactly the opposite. You have a nucleus. Sorry, I said atom before. I should have said nucleus. So you have two nuclei, you fuse them together. That's very difficult to do. With fission, you have one nucleus and you break it apart. So the process of doing fission is something that was really important to Oppenheimer. And what that movie is about, ultimately, is trying to come up with a way of breaking atoms apart and releasing the energy locked inside of that nucleus in literally an explosive way. One of the things that they talk about in that movie, Edward Teller, the guy who puts the sunscreen on, which is historically accurate, like he actually did that at that test.
Oh, did he? Really?
That was absolutely something that happened. That's real. They didn't make that up for the movie. There's actually remarkably little that they made up for the movie. We can talk about that if you want.
Yeah, I would love to chat about the accuracies and whatnot, and what you feel was more accurate and like even historical, right? So yes, please.
Sure. We'll circle back around to that. But in terms of fission and fusion, what Oppenheimer and the team at the Manhattan Project were trying to do was they were trying to actually break apart the atoms of a really, really big nucleus. So the uranium nucleus is the largest nucleus you find in nature. Okay? It's the last thing on the periodic table that occurs in a rock in the ground. And in Canada, we dug up a whole lot of uranium. The US also has a lot of uranium. Canada is oddly the second largest producer of uranium in the world.
Oh, I didn't know that.
Of all places.
Yeah, go Canada.
Go Canada. Yeah. Go Canada. So Canada actually, produced a lot of this uranium. The U.S. produced a lot of this uranium, and uranium is just an element like carbon or iron. It's a thing that exists in rock. It's something you can pull out, but it's the largest element we'd ever found. So historically, some of the scientists that are mentioned in the movies, and some other ones that actually weren't mentioned in the movies as well, were playing around with nuclei, trying to make them bigger. So they had their nucleus, and they were adding neutrons to see if they could make something bigger, and they wound up making something smaller. So what they had done was they had done fission. And that's actually something that they talked about in a newspaper article in the movie. So Oppenheimer is talking with Lawrence. All of these are historical people, and they come in and there's news of splitting the atom, and that was true. One of the few places where the movie was not accurate is the guy goes in the other room and then just immediately does it. Like that's not a thing you could do inside of 20 minutes.
Yeah, it's done in minutes. They say like scientists do it in minutes, and it's like that's not possible.
So
that would be amazing, but that's not true. Yeah.
I don't have a lot of complaints about the movie, but that's one. It's a quibble. It's a minor complaint. But what they were doing was they were splitting it apart. Now, Ernest Rutherford, that guy from New Zealand who moved to Canada, did his Nobel Prize winning work here in Canada before going off to work in England to make even more important nuclear discoveries. Rutherford, one of his students, actually first split the nucleus, but in a different way, and also first fused two nuclei. So we've been doing nuclear fusion in one way or another for a good 100 years, roughly, like roughly a century at this point. But we had roughly at that same period of time, it had been worked out that the sun was actually being powered by nuclear reactions. And the person who worked that out was actually one of the scientists in the movie. What powers the sun is taking small nuclei and ramming them together. What's tricky and difficult about fusion is that the force that you have to push against these nuclei, so as you're pushing these together, it takes roughly the same amount of force as the weight of a small dog, like a medium-sized dog, like a Springer Spaniel. So you need to be pushing on it with a force, like these itty-bitty tiny things need to be pushed on with roughly the same force as a dog is exerting as it's standing on the ground.
That actually doesn't seem like a lot, though. I would think that it'd be tremendously more, unless, again,
it
this is not my area of expertise.
You realize how small it is.
Fair. That's very fair. That's very fair.
Yeah. Right. So if you put this in human terms, realizing I'm doing this calculation in my head, but if you scaled that up to the size of a human, like if the force was acting on a human, it would be roughly the weight of the entire planet Earth.
Okay, I take back everything I said. So that's unbelievable.
So the force that's pushing these apart is roughly the same, like I said, as the weight of a small dog. Or if we were, if these were actually people as opposed to little tiny nuclei, it would be roughly the weight of the entire planet. But then if they get close enough, so they kind of bounce off each other, But then if they get close enough, the force that pulls them in is actually roughly the weight of a moose. And if you're not from Canada, that's roughly the weight of a grand piano. And if we're putting this up into human scales again, we're talking roughly the weight of Jupiter as opposed to Earth.
Yeah, it's unbelievable.
Realizing, of course, I'm doing all these calculations in my head as we're talking. So,
right.
But it's and that's why the sun shines. As the wonderful band They Might Be Giants said, the sun is a mass of incandescent gas, a gigantic nuclear furnace where hydrogen is built into helium at a temperature of millions of degrees. So the sun's been doing this for, close to 5 billion years. And that's what keeps the sun burning, is this fusion. We could do that, and we have done that. And what's interesting about the breakthrough technology, and we'll also talk about this in the context of the movie, the breakthrough technology is we can make fusion happen, but it takes a lot more energy to do that than we get out. There was a comedian named Henny Youngman, and one of his gags was, the easiest way to leave Las Vegas with a small fortune is to show up with a large fortune. You and I can go to Vegas, and I guarantee that we can win $1 million. It'll just take $15 million to do it.
Exactly.
Right? Fusion has been sure, we can make $1 million. It's just going to take 15. And I don't mean we start with 15 and we get 16. I mean, we start with 15 and we get $1 million out.
Right.
What's exciting about this breakthrough technology is every year we get closer and closer and closer to breaking even. So every time you do one of these breakthroughs in fusion, these are incredibly intelligent, hardworking people who have devoted decades to researching the best possible way to recreate what is powering the sun here on the planet. Can we do it? Yes. Can we do it easily enough to make money off of it, to sell? Maybe. Now, you've been hearing, we've been working, we first, fused two atoms, like I said, almost 100 years ago. So people start talking about when's it going to take, And after they had gotten the nuclear bomb, Oppenheimer got the fission bomb happening, people were like, well, okay, then, should be 40 or 50 years, and we're going to be good to go on the commercial fusion front. And that's just not what's happened. Fusion is difficult. In a world where we built the internet, in a world where we've flown to the moon, in a world where we've done all these amazing things, fusion remains hard and will remain hard, which doesn't mean it's impossible, but it will remain difficult. Now, getting back to the movie, what Teller was interested in doing, and he talked about doing, was building what's known as a thermonuclear device.
Right.
And what you have to do there is you have to actually make fusion happen. And the way that they make fusion happen, the way that they actually move these nuclei hard enough, is they actually set off a fission bomb. So the bombs that were the device that we saw explode in the movie, which historically happened in the deserts of New Mexico, happened very much like they portrayed it. Ed Teller really did put on the sunscreen. Richard Feynman really did sit in the car behind the windshield because he had done the calculation that the windshield would actually stop all the UV radiation. And he later bragged that he had the best view of the world's first nuclear explosion. So that's like a different scene. He's playing the bongos. That's also historic. Teller believing that we should be focusing on a fusion bomb rather than a fission bomb is also historically accurate. And he did go on to make the H bomb. That's what the H bomb is. It's a fusion bomb. But in order to get it hot enough to act like the sun, you needed to have the type of bomb that they developed in the Manhattan Project to actually ram these together to get the energy out. So what they're developing in the Manhattan Project is a fission bomb. You're taking a very large nucleus and you're splitting it apart.
Right.
And so what they eventually developed, and Russia also developed, with a fusion bomb. So if you take a conventional bomb, you can destroy a building with a conventional bomb, right? You pack a certain amount of TNT, and that is powerful enough to knock down a building. A fission bomb is powerful enough to knock out a portion of a city.
Yeah, I've read at least 1 million people if it was dropped on a major city today.
It would depend on which city, and actually,
Right.
truthfully, it even depends on things like how the weather's going. It also depends a lot on how people react, because people are so scared of nuclear and radiation that some portion of the deaths would happen just because people would flee the city.
That makes sense. Right. And fear as
So,
well, and chaos. Yeah.
so we don't have these up here in Canada much, but in the US, you'll occasionally walk by a building that will be listed as a fallout shelter.
Right.
And this is a place to go and hang out and spend time while the radioactive debris is actually falling out of the sky. So how much people like stay indoors versus go outdoors has a huge impact on how many people would survive a nuclear bomb.
Right, that makes sense. And we still see the nuclear fallout today within the Uinta Basin and parts of Nevada. It's still affecting them, since the 1940s. And it's causing major health concerns in those regions still. Yeah, which is really unfortunate. You see really high rates of cancer. There's rates
Um,
of we see still
yes and
deaths
no.
apparently. Yeah.
Yeah,
Well, I
yes and
believe
no.
that the Uinta Basin is going through a government looking for reparations right now, and they're going through that. I know
Yeah,
Utah is, and looking
the
for it from the Manhattan Project and other testing.
the birth defects thing is not actually something that's ever been shown. Like
No,
they've never.
that's fair. Yeah, but I think they say like from the nuclear fallout side, they're still on the that is potentially something that they're still debating right now, and I think they have been
They're
for a
certainly looking at
while.
it. It's
Yeah,
fascinating if you look at the maps, though, how you can if you look at the Kansas cluster, you can actually see where the border of Utah is,
right.
because there's other things like smoking, and Utah is almost entirely Mormons. They don't smoke a whole lot, so that the incidence of cancer is so much lower in Utah because of other health things. So it's really tricky to tease out where cancer is coming from and who has cancer. So it's one of these areas of research that is hard to do.
For sure. They
Um,
also have like one of the largest methane leaks in the nation as well. They've had
sure, which
that.
is
Yeah.
not wonderful for other
Exactly.
reasons.
And yeah, and can lead to those other health related causes too.
Yeah,
It's a lot of stuff
getting,
going on in Utah, unfortunately. Yeah.
there is, which is a pity because it's a lovely place. Um, but getting back to the movie, what what they're really focusing on there, and it's truthfully historically amazing that that team was able to do it. I mean, sure, they had unlimited, functionally unlimited money, and they had a significant fraction of the smartest, relevant people in the world. Like, it's not that there weren't a lot of other smart people in the world, but in terms of people who did this kind of work, a significant fraction of everybody who was qualified to be at Los Alamos was actually at Los Alamos. Um, Notable exceptions were people like Werner Heisenberg, who was also in the movie, and they talked, although not as clearly as I would have liked, about the fact that Werner Heisenberg, of the famous Heisenberg uncertainty principle, was actually working on a bomb for Germany.
Right. Right.
There was also a Japanese nuclear bomb project as well, but it turns out that the Japanese nuclear bomb project was not even nearly as far along as Germany's was, and Germany's was years behind where the U.S. Project was.
I didn't realize that the Japanese culture was working on one too. I never knew that. I never read that before.
Um,
It's interesting.
it's one of these things where when I look at it, there isn't a whole lot of clear evidence. It's like they were sitting around doing calculations on it. It's not clear to me that they were actually doing, um, and we're just hitting the limits of my knowledge. Like, I don't know how much are the limits of my knowledge and how much of the, like, I don't know how much. I mean, I know what I don't know, but I don't know how much of what I don't know is because no one knows, because secrecy and so forth, and was quite rampant. Germany, on the other hand, had actually begun experiments. Um, but they talked about this in the movie, where they talked about how Germany was going down the heavy water route as opposed to the graphite route.
Okay.
And there's a completely different movie about the heavy water aspect of Germany. So heavy water was actually in the process of being made in Norway, and some people were like, "Hey, let's go mess with that," and that was part of what prevented the German nuclear bomb project from going forward. But they also just they didn't have the resources that the American project did. Um, so yeah, all told, it was it was quite an exciting. Well, it's an exciting movie because it was a very exciting time. You asked me earlier how accurate is the movie, and the quick version is I could list off a few things that weren't quite right, but it's one of the most accurate movies that has ever been made on something this complicated.
Yeah, and the device too that was
Mhm.
creating the nuclear bomb was fairly accurate. Like the images were in black and white, and I've heard that it was like a peach color potentially from what I've seen and read in real
I actually
life.
didn't know that. Okay.
Yeah, that's what I've heard. And then but the accurate of the device of what they created, that shell around it was fairly accurate. And then along from even down to the way that the setup was from being outside in the desert and how they built that large tower and tent around it so that even the smallest amount of dust could have like messed up the entire explosion.
Yeah.
So or like put it off or did something wrong or some kind of malfunction. So
Yeah.
I believe like
Tricky,
Christopher,
tricky
yeah,
electronics.
very tricky electronics. And I remember when I watched the film and I was with a friend in there, I said, it's just insane to think watching this maybe from a perspective, right? Watching it and thinking like this is maybe somewhat accurate in scenes, but the less they knew now about like and how they went about doing the science and even the technology around it, and even the safety around it compared to how we are now, it
Mhm.
is so archaic in its own way, right? And it
Oh, it
makes
is.
sense because obviously of the time, but it's really interesting to see. It's like us going to space. I love watching anything from earlier space missions because you look at their computers and everything else and you're like, this is unbelievable compared to how, we're looking and working with fusion now. Can we
Mhm.
talk a little bit about how we work with fusion now and that we talked about earlier about the process of it, maybe being 50 to 60 years where we're looking at using it hopefully within a defense aspect or within preventing and helping, fight climate change. So where are we in, and I believe it's been accelerated, they've said. So where are we now with fusion technology? And then where are we looking for it to potentially become practical in our real lives and every day?
So the difficulty with answering these questions is just right out of the gate, no one knows.
That's true. Yep.
Um, so if you ask different people, you're going to get different answers because, in terms of what's going to happen in the future, it's guesswork for everybody. So I want to just open with that.
Yeah, no, it's
That
fair. I think from what we're hearing from other people and other scientists, because recently they've come out and said it will be 10 to 15 years potentially next decades. That's what I read actually today. And I was like,
Yeah.
whoa, it's such a quick, that's like December. We just came, this was just announced, and it's like June, July, where they're saying, oh, it actually is going to be sooner. So there are some conflict, and we see this in the science world, right? Of what might actually happen in theories, and how things will come into
So
practicality.
so part of the difficulty is you have to read the fine print about what it is that they're predicting.
Good point. Really great point.
Okay? So so there's a world of difference between successful bench test and electricity going on the grid. So
It's a,
um,
it's a massive scale.
it's a massive, massive scale. There are a number of people who believe that artificial intelligence and a lot of the chat GPT type stuff that's coming out is going to be able to manipulate the fusion situation in such a way that it will be able to control things faster than a human ever could. There are other people who are saying, people who know more about fusion than I do, because that's not really my focus. But when I'm listening to people talk about what is and is not happening with fusion, I'm not hearing consensus, right? I'm not hearing that all the scientists agree because no one knows, and we're all doing guesswork. What I can say is that it is physically possible to make fusion happen because we've been doing it for a long time. It seems likely that at some point we will get to a point where we can make fusion happen for less energy than it took to get into that. But even if you get to that, the economic viability is not automatically assured. And what I mean by that is just because you can get more energy out than you put into it doesn't necessarily mean you can get more money out than you put into it. It's likely, but it's not a sure thing. So various things like what kind of regulations are going to go into place, what kind of intellectual property is going to wind up being in place, what patents are going to charge who, how much to do what, what's going to get stolen. Have the angel investors come in? What do the angel investors control versus not control? Getting from bench in a lab to product that is being sold widely is really, really hard in general. And the more complicated the technology is, the more places it can go wrong. And fusion is arguably the most complicated thing humans are trying to do.
For sure. On a
Like,
large scale. But what about the bipartisan conversation? Because I know Oppenheimer wanted that too.
just
He
just
wanted
to
it. Yeah. No, go
just
on.
to, just to be clear, I actually think solving cancer might be easier than fusion.
Well, I hope that is possibility, and who knows, but cancer's big
But
business too, to its own degree,
but this is
Yeah,
what I mean. Like, it's big business, and ultimately fusion will be as well.
exactly. That would
Now,
make
I want to
sense.
make
Yeah.
I want to make a really clear distinction that what Oppenheimer, the movie and the person, is talking about and was involved with is weapons, is
Yes.
bombs,
National defense.
national defense or aggression. Like, you can frame that how you like. What we're talking about here with commercial fusion, we are not talking about national defense. We are not talking about bombs. We are not talking about weapons. What we are talking about is a power plant. So that would almost certainly be a stationary thing. I would love to be wrong about all this. I would love for fusion to suddenly be easy. But history's been quite clear that this is not a technology that is going to be easy to get to. It hasn't been so far. Amazing people have done amazing work and have made amazing progress about it. But we're not there's this image in movies, and this is one of the things I really liked about Oppenheimer, is that movie really captured the you've got a whole bunch of scientists who are making incremental growth by working as hard as they can, and we are wrestling the secrets from nature as we go along. Um, that's what it's going to take. It's going to take thousands of people, billions of dollars, and 100 years of research to sit down and make commercial nuclear fusion. And it's not just some just the Manhattan Project was the most expensive government endeavor as far as I know. And we need to fight climate change with the same ardor that we fought World War II, because the consequences of not fighting climate change are going to be worse than World War II.
Well, and I'll bridge back then to the bipartisan conversation, because that should be a bipartisan, fighting climate change should be a bipartisan conversation in
By,
all this. It really should
are you,
be.
when you say
And it,
bipartisan, you mean the American, like Democrats and
I'm
Republicans working together?
Yes, not
Okay.
Canadian. And so an American conversation, and also just a worldly conversation where people are working on this politically, but also worldly, right? Where we're contributing in the science communities. We see that even countries at odds, still their science departments and relationships still work together and collaborate to some degree, right? Their
Uh,
agencies still do. But
I'm I'm
yeah.
going to make a really offensive statement. No swear words.
Okay. Just to just to
But
should put a little sign up.
yeah, but there is no government of a developed country in the world that is taking climate change seriously. There is no political party that has any pull whatsoever in Canada, in the US, in any of the industrialized European countries, um, Australia, New Zealand, the wealthier countries in Asia. None of them are actually taking climate change as seriously as climate change needs to be taken. Zero. The Republicans don't, the Democrats don't, on this side of the border, the conservatives don't, the liberals don't, the Green Party does not, the NDP does not. There has been this conflation in people's minds between we need to have solar panels and,
Right.
and that's going to stop climate change. And we absolutely need solar panels. I'm not anti solar. But the amount of effort and resources that we need to devote to fighting climate change is so much more than any politician is willing to acknowledge, admit, and for the most part, even understand. So it should be a bipartisan, but it's actually a zero partisan, because
Right
neither
now.
Republicans nor Democrats are actually taking climate change seriously. And in Canada, the Green Party is not taking climate change seriously, and neither is anyone else. And when I look to the UK or France or Germany with their, we're going to revolutionize their energy, they actually drove their greenhouse gas emissions up because they were not interested in climate change. They were interested in renewable energy, and those are not the same things.
Right. And I did see that I read an article that Germany phased out nuclear power. I believe it was
It
like
did.
April 15th of this year. Yeah, I read that. And I thought that was interesting because that was in their thoughts of fighting climate change, I believe. But the
Yeah.
thing is that a lot of people I've also have read that are embracing nuclear fusion now and seeing that that would be potentially the way to fight it compared to what people thought in the past, right? Because of
Well,
nuclear fission. And
but
hopefully maybe that is the way, but I know
the
there's
problem
so
is
much
nuclear fusion.
politics around this, right?
Nuclear fusion is at the moment science fiction.
Right. Yeah. It's a
I
smaller
mean,
form, not to a larger form. Correct. I don't, but
so
why would you call it science fiction? Because it is still plausible.
commercial,
Yeah. But
commercial,
it's commercially science fiction. Yeah. But maybe is the better way of putting it. Yeah.
right? If you go back a few decades, much of what we do on the internet, like the phone call we're making right now over the internet, like I'm old enough to remember when that was science fiction, right?
Yeah.
So so the people who are actually betting on nuclear fusion as being a significant fight towards climate change, it's a gamble because we don't know that fusion's going to work. Like if I get on my bike and head home this evening, I'm relatively confident I'll get there. I'll be careful crossing streets and so forth. Fusion's not like that. Fusion's almost like buying a lottery ticket. It's such a risk to put our hopes on fusion. I'm not saying we shouldn't pursue it. We should. Although I am actually opposed to buying lottery tickets, just to be clear about that. I think the lottery is a tax on people who are bad at math. But 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 when it comes to fusion, betting the future of the only planet that humans can survive on technology that we have been trying to develop for decades and we keep hitting roadblocks, that is not a good bet. By all means, let's pour money into it. But we need to aggressively build wind farms, and we need to make sure that all of our hydropower plants are working as properly as we can and take care of the environmental consequences of that. And we need to build as many solar panels as we can. But at the moment in 2023, 5/6 of the world's energy comes from fossil fuels. 5/6 of all the energy that we use needs to be replaced, or we are going to have really catastrophic consequences. So even if fusion does work, we're still going to need wind and solar and hydro and geothermal and fission, because we need to actually take an all-in approach to what's happening with climate change, because climate change is so much worse than anything else that we have faced, with the possible exception, ironically, of global thermonuclear war. The, the only other thing that has ever threatened our species the way climate change is threatening us is unfettered access to this nuclear weapon technology. So it creates a real irony that I really do believe that nuclear technology, fission, and hopefully someday fusion, needs to be brought to the table as aggressively as possible, along with all of these other biofuels. I haven't mentioned those yet. Tidal power, ocean current. We need to take an all-in approach. And we need to, getting back to your idea of bipartisanship, we need to walk away from I'm a Republican, or I'm a Democrat, or I'm a Green Party, and say we got to solve this because we're all on the same planet. We also need to walk away from the American versus Canadian versus China, because it's one of the things I'm hearing a lot right now in Canada. I live in Alberta, where we have as much oil in Alberta as Saudi Arabia does. And one of the things that I keep hearing here is that it's not us, it's all China's fault. And we can't take that attitude about climate change, because unlike other types of pollution, CO2 emitted anywhere is a problem everywhere. So we've really got to be a lot more aggressive about this. And it's not just bipartisan. It is bipartisan, but it's beyond bipartisan. It's a global problem that requires a global solution. And while fusion might be part of it, if we're not looking at fusion technology being available for 15 years, that's when it's available. And then it takes 10 years to build. That's 25 years. The devastation that's going to happen from climate change on the timescale of a quarter century is people starving. The wildfires we've been having here in Canada this year, that's going to get worse. The floodings that have happened in Pakistan, other places, that's going to get worse. We're going to have a collapse of biodiversity if we wait for 25 years. Fusion's great, we should do it, but we can't actually gamble our planet on that working fast enough.
No, I agree with you on that. I love
And
how this,
that's my
no,
offensive rant.
no, I love that this conversation about energy and fusion and fission has turned into a conversation about climate change, because it's very true. We look at, climate refugees potentially becoming a really, really big thing, right? Prepping from all
It will.
different countries. And so,
Yeah.
and that can happen within the next decade. They're predicting 2020, 2030, they're saying. So as a Canadian, two Canadians talking over here with a lot of other Americans watching, they might be coming up to Canada and living with us. They might be coming to hang out with you in Alberta because of the drastic change. So I agree. I think we're supposed to have this evolving of looking at what we can use now and doing it appropriately through a bipartisan or global conversation. I do agree. And then also still working on new technology outside of any other advances of fission and fusion, outside of fusion, let's say, and outside of things like solar power and things we have. Are there any other advanced energies that are being talked about that would be more advanced of fusion right now? And I'm not sure. That's why I'm asking you, because I haven't even
So,
looked that up myself.
so the answer to that question is it depends on what you mean. So in terms of sources of energy, fusion's about as advanced as you get. But there are other advanced types of energy that are out there. For example, geothermal has some really, really exciting breakthroughs that have happened. And one of the things we're looking at here in Alberta, and I can't actually say too much about this, but we're actually looking at taking old natural gas wells and using the geothermal gradient in that to create, electricity or home heating and so like there's ways of turning things that already exist in advantageous ways. And like I said, I can't speak too much about that. But fission and fusion are not the only exciting places where smart people are putting a lot of effort into. Solar power has been making a lot of progress. There's a lot of amazing, interesting innovations and so forth that are coming out in the solar world. Wind turbines are there are smart people who are actively working on wind turbines. Hydropower, there's a lot of work that's now being done on micro hydro. So there do exist a lot of different, like ocean thermal electrical conversion is another one where, because the top layer of the ocean is warmer than something like 50 or 100 meters down, you can use that temperature gradient to make electricity.
Okay.
And this is, again, there are so many people who are working on this, which is great, but we need more because this needs to be applied. The other really, really big game changer, and I am one of the reviewers, I'm a very, very small fish in the reviewer of the Intergovernmental Panel on Climate Change that advises the United Nations. But one of the complaints I have about that report is that it acts as if climate change is going to be adequately addressed by carbon capture and storage. And I look at carbon capture and storage and I say that is also, at scale, science fiction. Now, I think we might be a little closer on carbon capture and storage than we are on nuclear fusion. But there was just an article, I think today, about a Canadian company that does carbon capture and storage being bought out, for over $1 billion. It was kind of a big deal. I need to look into it more. So this carbon capture and storage thing is another place where a lot of exciting work is being done. And if we can do that, then climate change is not going to be nearly as bad. But much like what I said about fusion, that's a heck of a risk to take for the only planet we can live on. Because it's not just the planet getting warmer. The planet will change in ways that it will be hard to grow crops. It will be hard to feed people. We will lose our homes. We will have smog that comes from these forest fires. It's not just about being hot. The hot is, if anything, I don't want to say the least of our problems, but it's not actually the biggest problem with climate change. Ocean acidification is another one. We could have an entire collapse of the ocean ecosystem as a result of climate change. So we've got to take this from a lot of different approaches, and a lot of people are doing a lot of different research. So, I mean, I don't know about all of it certainly, and I'm not the right person to ask about all of it. I can give you, dribs and drabs. But the other big thing to keep an eye on is this carbon capture and storage. Of taking CO2 either out of the atmosphere directly, which is the hardest way to do it, or taking it out of the fuel source or off the top of a smokestack. I mean, there's lots of different ways to do it. And then taking that carbon dioxide and burying it deep underground, where it can then be geologically stable, we hope. Should be. But again, and it's much like with the fusion, it's not like we haven't done this. The Boundary Dam project in Saskatchewan, that was successful, right? It was, the technology worked, but it costs money, and it's not free.
Now, my last question to you then, because we're talking so much about the Canadian aspect, are we working more with states or other countries right now in our development? You're a professor and you focus more in science and obviously in nuclear. Have you seen the collaboration and what's that look like from a North American perspective, and then also from a worldly perspective?
So for people in my world, the most exciting news about upcoming technology is not fusion at all. The most exciting technologies that we're talking about are small modular reactors. And these small modular reactors are I mean, they are also to a certain extent uh, science fiction, but it's more like 2 generations away of the iPhone. Like whatever iPhone you got right now,
Oh, it's
the
close.
the small modular reactors are like the 2 generations away. And the collaboration that I'm seeing on that is really exciting. What I mean by that specifically is the US government, the Nuclear Regulatory Commission, is working with the Canadian comparable organization, the Canadian Nuclear Safety Commission, is working with the UK, is working with France, is working with China. And all of these different organizations are trying to come up with ways of making the regulations easier to comply with. And then different organizations are also coordinating. One of the things I'm fond of pointing out is that this is a Canadian nuclear fuel bundle,
Nice.
roughly the size of a rolled up yoga mat, if you will. Um, and this rolled up yoga mat is enough electricity for a family of 4 in the US or Canada for somewhere between 100 to 200 years.
So that's unbelievable.
And
First
this
of
is what
all,
nuclear waste
that's
looks like. It's not green goo. The
yeah.
Simpsons have nuclear wrong. So this is what nuclear waste looks like. It looks like, metal, and inside you'd have, ceramic pellets. And so this is what you put into the reactor, and it comes out looking like this. So everybody's like, "Oh, nuclear is great. What do you do with waste?" The answer is you take something like this,
Can
you
that be
stick it.
reusable though? Sorry, I cut
Yeah, I'll
you
get to
off.
that. That's
Oh,
that's exactly the right question. So the current plan is that you take this out and you stick this in a pool of water, like an Olympic-sized swimming pool, and you do that for like, 7 to 10 years, where this becomes a whole lot less radioactive and easier to handle. And we've been doing that. And then you stick it in basically a giant warehouse. So above ground dry storage is what it's called, but it's basically a giant warehouse. And then it just sits there for 50 to a couple hundred years. And then the current and we're doing that. And then the current plan is to actually take this and stick it in a hole in the ground where it will just stay forever. But in Canada alone, there is $1 trillion worth of material inside of this here. Now this is empty, right? This has never. Now, not one of these, but if you looked at all 3-4 million bundles that we have in Canada of this, there is literally gold in there. So going back to what we were talking about with Rutherford and the alchemists, when you split apart uranium, you make other things on the periodic table. I kid you not, there's actually gold in there, and silver and platinum and other expensive stuff. We don't currently have the technology to get it out and use it. Again, it's science fiction. But here's the exciting thing. You asked about, is it reusable? Well, there's some companies out there, Terrestrial Energy, Moltex, these companies working in Canada and in the US and UK, elsewhere, are actually coming up with ways of getting 50 to 100 times as much electricity out of this. So instead of this being enough electricity for a family of 4 for over a century, this would now be enough electricity for an entire neighborhood for a century. And the radioactive waste, instead of lasting 1 million years, will only be radioactive for 700 to 1,000 years. And then at the end of it, you have more gold literally in your waste.
wow.
So we have exciting technology on the fission front. And I cannot imagine that fusion will wind up coming faster than these next generation iPhones, what we're calling the small modular reactors, that there are dozens of countries around the world that are currently looking at trying to build. And the collaboration that is happening on the international scene to make that happen, because there's a lot of us who are really, really scared about climate change. And we got to keep building those solar panels, but we can't just do it with solar panels. And we got to keep building those wind turbines, but we can't just do it with wind turbines. Climate change requires us to have a global mobilization comparable to what we did with World War II. And much like what Oppenheimer did to help end World War II, we're going to need to actually look at nuclear technology to figure out exactly how to stop climate change so that we can keep enjoying the planet that we live on.
I'm going to end it there because that is just a great way of saying it. And what a ride. that was a wonderful ride that you took me on, because we started from pop culture of science and within Oppenheimer all the way down to then fission and nuclear advancements in nuclear, and now to then what we're looking at potentially doing positive progression in fission. So that's wonderful, Jason. And as I say to my guests, thank you for being rebelliously curious with me today.
Absolutely. Thanks for inviting me on the show.